when you try to shear it faster, all the colloidal, sorry, in 沙拉酱这就是里面那些醋油醋 ，initially they are random, but when you shear it in this shear thinning region, all these little oil they will start to line up. It's just like a laminar layer, and that's easy. Okay, so that means the viscosity will drop. But if you crank it up, if you shear it even faster, you get chaos. Okay, so now the drop would aggregate into very different size. So eventually the viscosity shoot up. So this is a very famous example of the structure change leads to transition of different behaviors in mechanical behavior. Okay, so we found an analogy in our case. Okay, so that's another surprise in crumbling. Okay, a very simple system is much simpler than paint, than oil, but they seem to share similar relation. Okay, structure change leads to a mechanical change, mechanical behavior, different mechanical behavior. Okay, do I need a second joke? Does people fall asleep? Okay, right. Okay. Question? Okay, right. Joke?
Yeah, I
Okay, what?
When I look at your cartoon,
Yeah.
So you are assuming this length of this, the sticks are same.
No, they do not need to be the same. So the main emphasis of these three cartoons is how much ordering that appear. It's not how long the stick is. So in this case, there's no ordering, but in this case, they are all ordered.
Okay, my point is there's another parameter which is the length will be changed with the certain steps.
Yeah, agree.
And that this increase, that decrease the ordering.
Yeah, I agree. But
and then how this is surprising that this how they can be this follow this potential.
I don't know. I mean, this is just what we see, right? So I'm you're most likely correct because as I said, 我是掰的，所以他可能是猜对的，可是不要相信我，可以吗 ？Okay, so I just make it up. It looked like plausible, right? So I'm not 100% sure, even 10% sure. Right. Okay. So that's one thing about okay. So let me hurry up. So that's power law. So there are a lot of power law. You can see the power law. A lot of power law. Okay. The first one is very famous, 80-20 law. So that means 80% of the national income or the income of the world are controlled by 20% of rich men. And so if you plot the income in x-axis and the numbers of people in the y-axis, again, you get a simple power law. Okay, so that's the first, very famous. And the third one is the earthquake. Okay, and another one, let's forget this, is the power law. If you measure the activity of your brain, you can measure it. Okay, there are small activity, there are large activity. If you record it one day, you also get power law. Okay, so that's something that neuroscientists they have verified in recent years. And why that is interesting, so these are facts. So they are series. So this is the first theoretical model. This is by Pabak. Okay, Pabak is from Denmark. Okay, in 中文，这个家伙就是很屁的，很臭屁的那个。Okay, sorry, I don't know how to say that. This guy likes to insult people, so people said he's more American than most Americans because he's Spanish. Okay, yeah, you know, Dan people they are famous to eschew confrontation, but he likes to confront people. He likes to insult people. Okay, but anyway, so here's this theory. So you can read by the title of the book. He's very arrogant. He said he knows how the nature works. Okay, and his model is sand pile. Okay, imagine what sand pile is. You get sand and you try to sprinkle it. So what do you get? You start to get a tiny little sand dune. And by, you get avalanche. 沙会崩下来 and they come in very different scale. Initially, it could be 5颗, 5 gram, 10 gram, and eventually you probably get 20 gram, or 有时候会大山崩，有时候小沙崩. You just keep doing it, and then you plot how many cent it fall off in each avalanche, and how frequent it occur. You get power law. Okay, and this guy he claims that this model applied to all nature, including sociology, economy, high energy. Okay, you may think that I'm bullshitting. Hey, where's my paper? Okay, so let me read. Okay, because I copied this from the website. I just want to make sure. It says the Senpai model can be applied to sociology, quantum gravity, economics, plasma physics, neurobiology, okay, so etc., etc. So you may laugh. So that's why people laugh at him. I mean, he died at my same age. He died a long time ago, at 53. Okay, he has a hard time getting a permanent job. But after he died, in recent years, people start to agree with him. For instance, the neural activity, people start to believe in. So what is the lesson that you learn from this? Now people believe that our brain, for normal people, which means you had good sleep yesterday, you did not drink, but in Taiwan you already have drugs. Okay, so if you are healthy people, that's how people survive. That means you constantly have a lot of stress, a lot of stupid things. So the way you deal with your stress, it's just like senpai. You just let it off. You just postpone it. You just procrastinate. You just ignore it, little by little, and that's how you survive. So, okay, that's how systems survive. If you try to think of it, it's very similar. Okay, so the way the human try to adapt, try to survive. I mean, you don't have to commit suicide. You try to forget things, just like avalanche. When the stress builds up, you just let it go. You just let it go. Okay, so in a way, it's similar, but it takes a lot of years before people start to believe that they are indeed the same. Okay, so this is a very so if you look up the Wikipedia, you can just look at SOC, self-organized criticality. Okay, there are a lot of citations. Okay, so that means just like in critical phenomenon, usually in critical phenomenon, you have to tune the temperature, or in quantum phase transition, you have to tune the parameter. You have to tune it very carefully. But in this model, it's more beautiful. It's that you don't need to tune it. The system would spontaneously tune by itself, just like senpai. They will adjust when to avalanche. It's automatic. It's spontaneous. Okay, and this is non-equilibrium, so it's a dynamical system. Okay, so that's the beauty of this theory. Okay. Okay. Right. So there's another competing model. So this is cracking noise. So this is similar. You see, this is another topic that related to crumbling. So that cracking noise means this. So this is called cracking noise. Okay? So this is nature. So he tried to relate all the power law to a critical phenomenon. Because if you attend the statistical mechanics class, 第二学期, they will tell us that in phase transition, you also have power law, also the power law. Okay? And very different systems, sometimes they will share similar power law. And that's a signature of phase transition. So they believe that this guy, this is called James Sessner. So if you're doing condensed matter, he's a student of Phil Anderson. Okay. So they believe that all these different systems, they share the same universality class. Okay, so that's the theory. Okay, if you don't understand, I mean, just forget it. Okay, but that means they believe this is a critical phenomenon. Okay, so that's another thing. This guy works. Okay, let me see how I'm doing. And okay, so all kind of power law. This is in crumbling. So that's Tom Wheaton. So he's a student of 马尚根. Okay, that's 马尚根的学生. He's in Chicago. So you also have all kinds of power law. It says when you crumple a paper, they are all sort of fold. They are longer fold, shorter fold. So he used theory, he derived that if you have a fold twice as another one, it doesn't take twice as energy to make it. You only take 1.3 times the energy. So 你把你折这么长要费的能量是1焦耳，你用2倍长不是2焦耳，只要1.3焦耳。Okay, there is the power law, and there's also power law, but anyway, so this is also power law, also in crumbling. Okay, how energy distributed. Okay, so you can also derive that. And do I want to do this? The answer is no. Okay, so this is another thing, another property in crumbling that is very interesting. Is if you do a statistical mechanics, you record this. Okay, so that's more. So you probably have, I don't know, 700 folds in here. Okay, they are longer one, short one. So you x-axis is the length of the ridge. Y is how many are there. You get a distribution. No power law, but you get a distribution. And it turned out not to be Boltzmann. Okay, you will ask me, what am I talking about? Why do I mention Boltzmann? Because people would ask, in order to create this fold, you have to do work. Okay, that's stupid, of course. But after I do the work, I leave this. So that means the work is conserved. So this is the energy conserved. It is energy. This is the adiabatic system, just like our room. But in this room, you know, if you catch the air molecule, you measure the energy, it's Boltzmann. Why? Anyone want to answer? We have souvenirs, so if you can ask the most questions, you can get a gift. For energy conserved system, you will try to increase the entropy. And to get maximum entropy, the particle energy will not be the same, and they have to follow Boltzmann. And in this case, it's very similar, because the energy you input is already fixed. And the longer fold look like a hot particle, and shorter one look like a cold particle. But in the end, it's different. It's not Boltzmann, so that's another puzzle. It looks similar, but the distribution is very different. Okay, so that's another challenge. How do you explain this distribution? So that distribution looks like that. It's called a log normal distribution. So that's the puzzle. Okay, if you can solve it, you get PIR. Okay, right. So that's more power. So that's more power law. So let's forget. Okay, so a lot of power law. Noise. Where is it? Okay, so that's noise. So noise is another problem. The statistical mechanics of the noise. So imagine. So this is plastic. Okay, so I input a fixed amount of work, and I just leave this. Can you hear the cracking noise? Okay, imagine, okay. So, don't you think this is just like earthquake? Because in earthquake, the different tectonic, different plate, they emerge and compress each other. So a lot of strength was built up, but no one can move. They stuck, right? And then once in a while, they will slip and they release energy in the parts, but then they stick again. Okay, just like in this case, because I input a certain amount of work and then I let my go. And then this guy tried to release the energy in the form of noise in pulses. Sometimes it's large parts, sometimes it's short parts. Can you see the analogy? And it turned out the power law, the power of this simple thing is identical to earthquake, to 瑞士规则的那个 power law.
Do they have the same exponents?
Yeah, it's between 1.5 to 2. Okay, so that's another thing. People are very surprised. So how does this thing because this is apparently much simpler than 地质学. Okay, how does this thing get exponent, and why does exponent fall in that range? That's also another unsolved question. Okay, can anyone see the analogy? So it's sort of they release the energy in a stick and slip manner, and how does statistical mechanics choose this power law behavior? Okay, so that's also another puzzle. Question? Okay, so that's okay. So okay, that's our simulation, because in our lab we do experiment, we do theory, we also do computer simulation. So I don't have time to explain that. So let's just forget that. Okay, right. So let's come back to this. Sorry. This is more interesting because this is real painting. Okay, the crumbling is interesting, but this is the cat, right? This is more cute. Okay. Right. So traditionally, in National Dance Museum, they have a lot of paintings, scroll paintings. They can be dated back to almost 2,000 years, 6朝, or even earlier. And as you know, Chinese painting, they are always stored in scrolls. So this problem is very popular. Okay? And so that I've shown that. So there's a lot of study, and they have all sorts of theory, but they're not from scientist point of view. They're from mechanics point of view, from empirical point of view. So they're not scientific, and they're hard to control, and they're mostly cannot be reproduced. Okay? But that's how people come up the wisdom in the past 2,000 years. Okay? 不错，你还看得懂，可以吗？这个文言文。Okay, right. So this is how people do. You try to put glue on it before you mount it, and that's detailed. The big style is called a calendar. Calendar 不是那个月历哈，最后改成倒数第二个改成 A， 你去查啊 calendar 就是 after you have mounted the paper, you use the big stone, you try to scrap it. It's called calendar, very similar to 月历, but with the A in the end. It's called calendar. Okay, so the way traditionally how both Korean, Japanese, and Chinese, they have different ways of doing this mounting. And normally they're secret. Sorry, no offense to ladies. Okay, but in old times, this is a very lucrative secret. So they only pass on to sons, no daughters. Okay, daughters no. Okay, only son can learn the secret. So this is passed from generation to generation. Only the eldest son. So this they're also secret. Okay, also secret. And different branches they never talk to each other. Okay, so that's how the situation is. Okay. And as you see, they are all paintings, Oriental paintings. They are normally stored in scroll. Okay, right. Okay, so about the right time. So let me see what do I want to do. Okay, right. Right. See? The reason why we think this problem is sort of a great opportunity for us to make big work is because we don't trust it. Why? Because people in the past 2,000 years, even now, they were convinced that it's a paste, or it's a 装裱师傅的技术, or it's the weather, humidity, all sorts of things. You can see, 这是plastic, right? So I screwed up, and 这边有没有这个社会正义人士，你可以来证明，4个边都翘起来了。I don't know whether you can see it. Yeah, right. So that means you get edge curling in these little things. So that means they are all talking nonsense. It has nothing to do with paste. And definitely, it is immune to humidity. Right? Okay. So that's how we prove it. Okay. See? You get curling on all 4 sides. Okay. So that means the curling is much simpler. It's the physics. It's the mechanics. It's the second-year mechanics problem. Okay. The origin is much simpler. Okay. So that's key, okay? So that we know they are talking nonsense, so we know we get a good work. Okay, now the next problem is how do you sort of explain this phenomenon in a more quantitative, in a more entertaining way? Okay, 我把这个传下去，你可以自己看哈。你把它打开，4个边你都可以看到，它就自动会翘起来。OK。Right. So now you get the idea. Now the next question is, what is the physics? Okay. So forget all this. Let me try to explain the physics. Okay. Because this is the main topic of today. So I hope when you leave, at least you can bring home something simple, a picture. So the mechanism we come up with is this. This painting. Most of the time, for instance, in National Palace Museum, most paintings, they are in exhibition no longer than 1 month a year to protect the painting. So that means more than 11 months they are being stored, okay? And because most of the time they are being stored, they are plastic deformation. So that means this thing is just like the plastic. They like to curl up. So there is a extrinsic curvature. Sorry, excuse me. 我考一下，你们谁有上过这个陈玉老师的因数 intrinsic, what's the difference between intrinsic curvature and extrinsic curvature? 哪一个数学比较好 ？Curvature 有2种，一个是 intrinsic， 一个是 extrinsic. What's the difference? 你画一个三角形 you draw a triangle. If the sum of three angles is not 180 degrees, that means this surface has intrinsic curvature or extrinsic curvature? Okay. 你要跟陈玉超讲 that's intrinsic curvature. So for a sphere, you have intrinsic curvature. So the easy way to check it, you draw a triangle and you measure the three angles. It will not equal to 180. But for this scroll, it will be 180. So that means for a scroll, the curvature is not intrinsic. So it's called extrinsic. Okay, it has curvature, but the triangle would obey the 180 degree. Okay, right. Okay, so now back to physics. Most of the time, you roll it up. So that means the back side will be the outer layer will be stretched. Okay, outer layer will be stretched because they are. Okay, right. So the outer layer will be stretched. Okay, when you open it. Okay, so to demonstrate it, this is paper. Actually, most of you, if you 在国中、国小，你有做过教室后面的壁报的时候，你一定有遇过这个现象。大部分壁报纸买回来的时候，打开旁边都会翘起来，我不晓得你们有没有印象。So most posters, or at the end of the year, people would send you a new calendar. When you open it, you get curling on both sides. So how does people do this? If you sort of try to roll it the other side, can you solve the problem? No. If you do it this side, you become wavy. 会变成海浪状。我不知道你们经验。你反过来则没有屁用，没有用。没有用，对啊，你刚听错，没有用。OK。所以你可以看 ，see， 好，是纸，它也会翘起来。Okay, so that back to physics. So that means when you store it, the outer layer will be longer in the length, 在长边会比较长，所以是下面 the outer layer will be longer. 你帮我一下把这两边压住。So when you compress it, you force the bottom layer to be of the same length as the upper layer. That means the bottom layer will be squeezed because originally it's longer. So you're squeezing the bottom layer. When you squeeze it this way, 跟吃红豆饼一样，你用力咬下去为什么会爆浆？有没有？哈。So you squeeze it this way, you will try to barge out on this way, the bottom layer. So the bottom layer try to barge in this layer. That's why you get curled up. See? 下面这个比较长，它是不是自然就会压起来？咦，有没有？就这样子，我们就这么简单。OK。So you can see the 宽边 this is shorter, right? See? If I decrease the width, the height will decrease. So you can expect a simple power law. So this guy would be proportional to the length of the width, but independent of the length. Likewise, this curve is much smaller than this guy, but this guy will be insensitive to the width, but it would be proportional to the length. So the next question is, if this is longer, why does this guy curl up much lesser? So the physics, as I just said, this side, originally, the bottom layer is longer, but because we try to force it to be the same length, so 底下那个不爽，所以它就翘起来了。So that's this guy. But for this guy, you need to have a intermediate step. 你需要那个爆浆的过程 and that's called Poisson ratio. Because you're squeezing the bottom side, so through Poisson ratio, it bulge out the bottom side on the width, and Poisson ratio is normally 0.2. Okay? For incompressible solid, it's 0.5. But in realistic material, it's 0.2. So that's why this is much smaller, because this guy will depend on Poisson ratio, but this guy is just direct a function of the extrinsic curvature. Okay? So that's the physics. Okay? Okay, so that's simple. So that's that. Okay? And so how do you, so the next question is, how do you solve the problem? I mean, how would you say to 故宫说你要怎么弄你才能解决这个问题 So let's come back here. Okay, so okay, so come back to my physical mechanism. So the bottom layer gets squeezed. So the bottom layers try to bulge out on both sides. So initially, you expect this side to curl up, just like that. But notice, 这是平的. So that means actually it only curl up on a very little strip. 大部分地方是平的. So now you want to ask, 既然这个要爆浆，它为什么不整个翘起来呢？所以你反过来想，因为你整个翘起来的时候，这边是不是特高？特高它一定不爽，为什么不爽？因为这个特高的时候，这边就会拉。So there will be a stretching energy in this direction if you bulge out just like this. So to decrease the stretching, they try to calm down, but calm down they need to pay a price because I said there's a Poisson ratio. So this guy want to curl up, but if you force it to lie down, there will be compression energy in the middle in this direction. So that means there's a two energy. Compression in the middle is along the width, but in the 起瓦的地方是 along the length. Okay, it's slightly complicated. Okay, so in order to decrease, in order to sort of 减轻这个翘起来现象，你要跟故宫要怎么讲？你不能说翘太多，那把这个长减一半，不行啊，被枪毙可以吗？ You cannot change the length. You cannot change the width. You cannot change that. So you pretty much have nothing to do. But there's one thing. Because this guy will come up. So if you can increase 把这个方向的弹性系数把弹簧变硬，什么弹性系数 ？The spring constant in the 起瓦 regime along the length 硬一点，它就翘不高。OK。 那中间也不爽啊，中间不爽是往哪里？不是往这里哦，是往这里，因为 Poisson ratio 要往这里走。所以同样的，你要把中间的 stress 要减轻的话，你要把中间的弹簧哪里沿着宽的方向把它减弱。现在听起来有点复杂，我再讲一次哦。你要让这个翘的不要那么严重的话，你要把边边的弹簧沿着长轴方向加强，把弹簧变硬。In the meantime， 把中间 沿着垂直，沿着 Y 方向减弱，这两个的话就可以让它翘。大家注意一下，那这样怎么办？这样你只要让